Hey guys, welcome back. Now today we're going to talk about a door. Now this is a top view. You can see that there's a pivot over here and this is the length of the door. What we'll talk about, let's just highlight that in a quick second. This is my pivot. Pivot. Now pivot is just a fancy way of saying that is just held there by something. So you can assume that it's just nailed there. So it's not allowed to move anywhere. It's allowed to rotate from here freely, but it's not allowed to move at all. So whatever is going to happen to this object in any motion is going to be about this pivot as it moves around. Moves around this particular point right here, the pivot. Now there are other names for it, like a fulcrum or something. Let's just call it a pivot. This is not the part to focus on, right? The idea is it's fixed. And what you've probably realized is no one ever opens a door pushing it through over here. Mostly why? And you also realize the handle for a door is, let's draw a handle. I feel like channeling Picasso today, right? It's always on the edge. Have you ever wondered why? Right? Now, the obvious question is it's just easier or something. But it's also actually easier. By that I mean is it's much easier to open a door if you're pulling it or pushing it from here rather than over here. Rather than over here, the previous arrow, right? And the reason for it is the further away you're pushing away from the center of rotation or the pivot, the easier it is to push. So this is when you push something which is held on a pivot, you're causing it to undergo an effect, which is the turning effect of a force when something is held, right? So you're causing a turning effect on this thing, and that turning effect is much greater as you move further and further away from the pivot. So the other way to increase it is the larger force you have. So if a much stronger guy pushes it or opens this door, that he'll definitely be able to open it. Let's assume this is a very heavy, rusty door. So one way of doing it is the higher the force. Let's put that down. So if the force happening on the affecting the door is F, so the larger the force, the larger this turning effect. So let's also mention that over here. The turning effect. Sounds so fancy when you call it that. Turning effect. And let's just move our force to the side. Is equal to. So the greater the force, the greater the turning effect. That much is pretty much understood. But also what I'm trying to say is the larger the distance between between the pivot and the force where it's applied, let's call that D, right? The larger that distance is, the also larger the force. So not only the force is proportional to the turning effect caused by that force, it's also how much the distance there is distance. So I'm going to put that here. Also distance, small d for distance. And a turning effect can be quantified or can be measured or can be calculated just by multiplying these two values, right? If this is 1 meter away and the force is acting on it, the turning effect is F. But if the force is 3 meters away, let's say over here, and you apply the same force, so that's F times 3 meters, so your turning effect will be 3 times greater than what it was over here. Continuing from our discussion from yesterday's slide is turning effect of floors, turning effect of forces, and we have another example for you, which is a seesaw. A seesaw. There you go, you have a seesaw. All right. So let's say Someone's sitting on the seesaw and they have some weight. They're pushing it down with some weight. Let's go with they're pushing it down with their weight or a force of 100 newtons, right? And the other person, way matching their weight, is also 100 newtons, let's say. But the difference you can clearly see is one is just kind of like halfway between the extent of, well, halfway of the entire board would be where the pivot is, but halfway from the pivot to their edge, right? They're somewhere around 50%, slightly more. They're slightly away from the 50% mark. This guy is all over on the other side to the end. And my question is, which way would the seesaw turn? Now, it would either turn clockwise, like that, or it would turn counterclockwise. What do you think? Now, we just talked about this. We practically wrote an equation down. But just by looking at it, what do you think who should be able to win from your own experience? And you probably are arriving at the right conclusion. What you've also realized is when you're, like, let's say, playing on a seesaw with someone who's much younger, you've realized that to kind of both of you to kind of play together, the heavier person, namely you, needs to sit much closer, and the lighter person needs to sit much further away. And the right amount of distance combination for the both of you will allow you to, enjoy the seesaw. I don't think I'll get tired of saying the word seesaw, right? So, but why is that happening? Because the further you are, again, the further the turning effect of the force. So if the lighter person is over here, let's get these forces out. Well, in this particular case, the seesaw will turn clockwise because this guy is much further away. But if you have a baby sitting over here, by that I mean much lighter weight person, and you have a normal sized person sitting on the other side, and let's go with you, right? You'll realize you'll have to move closer and closer to the pivot because you want to minimize your turning effect on the seesaw, where the baby has to maximize it because the baby is much lighter. He can't generate a lot of force. You, being probably 10 times at least heavier, needs to minimize your turning effect. And this turning effect you see in multiple things. And let's take a look at more examples. Even further continuing with our lecture, we're gonna talk about examples of this turning effect which we keep using, right? Now, over here, we realize that you want to focus on this part, right? This is the part where you want to apply force to, right? And you're pushing it from here, and the pivot is over here. It's a very short distance, very long distance. What is the equivalent output of your force? Is it going to be like the force on this paper? Let's just call it paper, what it is, right? Not load. When you apply the force over here, is this going to be much higher, much lower? And we can calculate that, we can figure it out. But let's try to develop a more like an intuition for this, right? Now, if you've ever tried cutting something, you realize that depending on the scissors, some scissors are like completely horrible, but you realize that the further something away from the blade is, or away from the pivot is, the harder it is to cut. Now, sometimes you probably prefer that because you're either cutting something really small or cutting something like, it gives you a little more control when you're cutting it from here. So you might want that. I'm not saying, you always choose this part, but if you're trying to cut something really tough, like a piece of rubber, leather, I don't know, right? You'll try to cut it from here. You'll automatically realize it cuts better if it's here rather than over here. Why is that? The closer to the fulcrum it is, the greater the force that's being generated by the force you're putting it over here. And we'll work on that. But you're automatically doing it naturally without doing the calculation. And be aware of that, right? You're doing this all the time. Now, this is one example. Let's move on to another one. And we shall bring in with us, right, over here. Now, this hammer or this part of the hammer is specifically designed this way because this part is not coming out too much. I mean, it's a lot smaller. It's exaggerated because it's a cartoon, right? And just to show it to you. But the handle is much longer and you realize this is much smaller. And you also realize a lot of force is required to pull this nail out from the ground. Now you can take a pliers and you can try to, pry it out, but what happens is you're just not able to. Even with the plier, when you're doing it, you're twisting it out and you're trying to give yourself that mechanical advantage. Over here, the same thing is happening. The pivot is over here. So even though it's bending like this, this is kind of acting like a bent seesaw. So this is where you're applying the force over here. And this is where the pivot is. Why am I using pink? The pivot is over here. And the handle, or where you're applying the forces, over here. This length is acting like one part of the seesaw, right? Oh, I wish I could draw it a bit neater. Now this length over here, speaking of neater, is acting as the length of the seesaw from the pivot. And even though it's not completely horizontal like how a seesaw is, or like our door example, the other part is over here. And it doesn't matter where it's angled. All the forces you're dealing with could be all on the same side or on opposite sides of the pivot. Doesn't really matter. It's all about turning. And because you're pushing it over here like this with a force F, but this D is much larger over here, and this distance is distance 2 and distance 1. Distance 2 is much smaller. The force being generated over here is much, much larger, and that allows you to slightly easily pull the nail out. Now, this sort of thing is your first introduction to machines, right? Like how a machine, how it's designed, can give you a specific mechanical advantage, right? And it's all about mechanical advantage. A lot of people, when they're introduced to this, isn't the force being lost? Or where's the force being generated from? Where is this magic coming from, right? Like, why is there extra force over here? And it's not like there's extra force over here. And you'll kind of, this sort of thinking will start falling into place in the next sequence of chapters. I can't really discuss that now, that how magically new force is being generated. There's no such thing as a law of conservation of force, right? It's not like wherever the force is, it'll always be the same. So this turning effect kind of can amplify a force or really decrease the force depending on how you arrange your seesaw or your any lever, essentially. This idea is not new, and it's very old, and some of the basic tools from back even in the caveman era had such designs, and the first machines or first basic machines or tools are born on this principle. Archimedes, I think a Greek mathematician and philosopher, once said, "Give me a lever long enough and a pivot on which to place it, and I can move the world." Which he's trying to say is, as long as I have a long enough lever or like long enough stick and somewhere to put a fulcrum somewhere or a pivot somewhere, I can, put the world somewhere and I can move the world. No matter how, small I am, if the lever is long enough, I can do it. And that's true, so to speak. I guess you can do it. Never been tried before, so I won't vouch for it, but I see no trouble in why it can't not. Or at least that idea can stick with us that no matter how big something is, it can be moved. What you've like, a few days ago, I had a Avengers binge watch movie, and being a physics teacher that I am, I would notice these things every time a strong Avenger like the Hulk or Spider Man, if they were, a building fell on top of them, they'd be trying to lift it like Superman, Okay, like fine, the Hulk, right? Do a, they'll try to lift the entire building above their head. But if it's someone who's like a normal person, like let's say Tony Stark, Iron Man, without his suit, if a building fell on him, like there were actually 2 or 3 scenes. I actually taught Tony Stark himself with like a huge debris on his leg or something, and he was trying to get out. And what he would do is grab a stake, stick it there, and kind of, you know, use it as a lever and pry the thing, lift the thing enough so he can move his feet out of the fallen bricks, or I think there's a word for it, the debris, right? And that is something I really liked, which was that all the people who didn't have the bronze or didn't have the strength were using smarts to, work around and do things. Anyway, so we were talking about turning effect of forces, the turning effect, the turning effect. Now, this turning effect, from now on, we'll give it a name. We'll call it the moment. Weird name, but whenever I say moment, you should think turning effect. Now, the moment is understood as the product of the force applied to a lever and the distance the force is applied away from that pivot, right? So the force, and let's say distance. Why am I not writing distance? Right? And let's turn this into an equation, which it already is. But we'll use capital M from now on. Force times distance, right? And it could always be either counterclockwise, this is counterclockwise, right? Or it could be clockwise. The motion of, or the result of a turning effect of force or a result of a moment can either be counterclockwise or clockwise. And we'll use this equation to solve any turning effect problem we come across.